So now, okay, good. So today we are gonna continue our discussion on these different areas of the design of a facility. On Wednesday last week, we started discussing the design requirements in terms of structural system performance, enclosure systems, and also atmospheric systems. And that's where we stopped. We started the discussion in terms of the design for a HVAC system in terms of capacity. How do you estimate the amount or the capacity that you need for your specific facility? So we're gonna go back to that part of the lecture, and we're gonna go back and review the exercise that we started discussing on Wednesday, and then we're gonna continue our discussion. So for any questions so far? So when we talk about atmospheric systems, we are designing because we want to provide for the health and comfort of occupants and for the needs of building equipment and machinery. So I brought the example in terms of computer equipment that you have to have some specific temperatures so the equipment can work well. Like for example, if you have a server or you have multiple servers in your facility, you need to make sure that this equipment generates a lot of heat, so you keep the temperature in that room within a certain level. So it's not just for the employees or the staff, it's also for some of the equipment and machinery that you have in the facility. Also, maintaining the work environment. So in terms of codes, they require only a minimum indoor temperature in winter. You want to provide that minimum temperature inside the facility if you're in a very cold area, making sure that you have a heating component that keeps the building within that minimum. Market standards for different building types provide more precise responses involving cooling and also humidification. So for example, in healthcare facilities, we need to make sure that the humidity is held close to 50%. And that changes according to the application or the industry that you're looking at. A more significant problem is the introduction of inorganic chemicals. So we talk about pollutants into the building atmosphere from sources in the building. So we talk about the idea of introducing this from different sources, through the windows, through the walls, through the ceiling. So we want to make sure that if we are building some specific high-tech or any type of product, that we keep these pollutants outside the building. So the major air quality problem is most buildings in the buildup of odor and airborne particulate matter. And the rate of dilution is expressed in terms of feet to the cube divided by minutes per square of floor area. So one can see that the way to eliminate unwanted substances is to dilute them by mixing stale air that is in the building and by adding fresh outdoor air. And I mentioned that's a system that is already being used in homes as well, not only in facilities or manufacturing facilities. So that's also being introduced to homes right now. So you want to make sure that the air or the indoor, the inside of the facility smells well, and also that you keep a good quality of air inside the facility. So you want to also design for those purposes. So we talk about the air exchange dilution rate. It's typically expressed in air changes per hour and is stipulated by local code requirements, depending again on the type of building and the type of use that you're giving to an area of the building. So here in table 1, we have different requirements in terms of air exchange rates for several building use types. You will see for example, there's a supply and an exhaust. So basically taking out the air from inside the facility. And those requirements will change according to the type of use that you're giving to the area of the building, in this case, the residents. Or if you're looking at commercial, school, a hospital, so you'll have different type of minimum requirements that you have to make sure that you meet. The equipment to bring in the fresh air and remove stale air is primary consideration in planning a facility. So we have to plan for at least a space in which this equipment is going to be located. So for those reasons, we need to be aware of what will be the requirement, so we know the type of equipment that we will need, and we can plan for that space and location. This space requirement is governed by the size of the equipment room. So depending on the type of building that you're designing, you have to make sure that you leave some space to place this equipment that you're gonna need. And this table is showing you some of the percentage of area for the equipment rooms. So residential 2%, office, industrial 5 to 7%. As you go down into this list, you see how those requirements increases. So for a laboratory, you're dealing with a lot of chemicals and organics and inorganic matter. So you have to have more equipment. Same thing for animal laboratory. As the air exchange rate increases, the handling equipment also, the area for that handling equipment also increases. So the more you need this exchange, exhaust, and inputting this air inside the facility, the more space you will need, because you will need more equipment. And here's some additional information about the design. This is just for your information. You don't have to memorize these numbers, but it's information for your, in case in the future you need it. We talked also about the clean room. So we have a clean room facility here in the RFM building. The idea is that you have a very closed environment in which you keep any matter or any substance that can affect the manufacturing of certain products. So facilities planners are often called upon to design a carefully controlled environment for electronics, pharmaceuticals, and food processing operations. So typically what you're going to have here is a very constrained environment. You have these filters that are purifying the air inside the control environment, and they are known as clean rooms. One widely recognized method used to achieve these air quality levels is the use of these high efficiency filters. With COVID, that became very not popular, but people got aware of these designs because of the need for limiting the spread of the virus. So these type of filters were used frequently in inside the airplanes and in other areas, closed environments. Those filters are used in a wide variety of industrial, commercials, and institutional installations where the highest possible degree of air cleaning is required. And then the last part that we discussed was the HVAC designs. The purpose of heating, ventilation, and air conditioning HVAC is to control temperature, humidity, and cleanliness of the environment within the facility. So the input required by an HVAC expert to design an HVAC system includes the facility layout and the construction specifications. So facility layout in terms of locating this equipment, and also depending on where you're going to locate the equipment, you know that the ducts that I show you in the previous slide are going to be designed according to the location of the equipment. So the facilities planning should be able to provide the HVAC expert with this input. understand how the HVAC expert translating this input into the HVAC requirements. So here's the type of information that as facilities planner we need to know. The heating requirements for the facility is referred to as the heat loss and is calculated using this equation, which QH represents the total heat loss. And we are accounting for different areas or different items that will be used to compute the total heat loss. So we're considering the heat loss through the floor, the roof, the glass windows, the doors, the walls, and the heat loss due to infiltration. For the infiltration, we are basically accounting for the area of the walls and the area of the roof. Okay, so infiltration can occur through the roof and also through the walls. So we are accounting for the area of those two components. So here's the equation that we use. Q equals AU times the temperature difference inside versus the outside. So the inside is where we're gonna try to keep at a certain temperature. Outside, in this case, since this is a heating loss, we are trying to, the outside is gonna have temperature. We're gonna count for the outside temperature, which is typically lower, and we're gonna try to keep the inside at eye level. Yes. So the difference you see for each component of these parts, we're gonna have a coefficient of transmission, and it's gonna be based on the materials that you're gonna be using in the construction of the facility. And that coefficient is gonna be based on the type of the item that you're looking at and the material that you're using for designing that. So when we are looking at the walls by themselves, we are looking only at the area of each wall and also the materials of the wall. Yes, exactly. So as you can see, the roof is gonna have, and we talk about that at the beginning of this lecture, there's gonna be different type of roof designs and different materials that you can use for reflective purposes. So that's a good question. So yes. So the infiltration is looking at something, it's considering the area of both the roof and the walls, and also looking at the materials combinations for both. And that's why I provided, because that was a question that was asked at the end of last lecture. So those, and you'll see why, in the problem that we started discussing last time, there's information about the materials, information about the size of the wall, and we didn't use that for the solution or for the computationals that we were doing. The reason why is that what we need that information in order to obtain the right coefficients of transmission for the facility. So depending on the size of the wall, depending on the material that you're using, you can go to this link and you'll see that there's information about different sizes, the materials, and then based on that, you can obtain the right coefficient for the facility. Okay, so that's why I added this. I'm not sure if in your slides you have this link, so I might need to add that to your slides, but can click on this, see if I can get there. Yeah, the idea is that if you go there, this is just one of the one link that you can use. If you search online, you'll find different sources, and it will give you the information in terms of the material, the size, if you're looking at windows, doors, and so on, and you can get this coefficient of transmission based on that. And then TI is the temperature inside the facility, and temperature outside the facility is T0. For air conditioning requirements for a facility, we have this expression to compute the cooling load. And here we are considering some additional components, such as the ventilation, radiation, the lighting, the personnel. And for the cooling, along for the solar radiation, you're using I mean, that we are using the same expression for these components. The only difference now is that instead of having Ti minus T0, you have T0 minus Ti in the cooling equation. I apologize for that. And for these two components, we have a different equation for the cooling load for solar radiation and for the cooling load for the lightning. I searched for the information for LED, which was another question that was asked. And I was not able to get the parameters in terms of BTUs and hours, watts. I was able to get it in the different units, different units. I think it was the international system. So I needed to change that to this. Wasn't able to do that, but I'll provide with that information as needed for the LED. But for now, we have the incandescent and the fluorescent for the computational purpose of the exercise. So for the cooling load from personnel, this can be calculated according to the number of people that you have, and also according to the gender and the type of work that you're doing. So depending on the gender and also the level of work that you're performing, you're gonna have this heat gains in terms of BTUs and hours. So this is the example that we started, we discussed last time. This is for the heating. So we have a facility, and as you can see here, we have information about the size of the facility, the height, 8 4x8 double pane glass windows, and 2 3x8 glass doors on both the front and back sides. The facility, so this is the information that I was referring to. It was made by 8 inches solid cylinder block and 1 inch metal insulated roof with insulated ceiling and insulated slab floor. So all that information was provided in the problem, but we didn't really need it because I was giving you that information for the coefficients. And that information was given for the purpose of the problem. But if you need to get those coefficients for a different type of facility, then you need that information in order to get the coefficients, okay? And the link that I provided you, it includes the list of coefficients according to the materials and the type of facility that you're designing. So we went through the process of computing the Q parameters for the floor, the roof, the glass windows, G, the doors, and then the walls, and also for the infiltration. And again, includes the area of the roof and the area of the walls. And then we added the total. So in this case, the requirement capacity in terms of this heating for the facility was 26.51 to the 10 power of 5 BTUs in hours. So here's where we stop. Today, we're going to look at a different example. This is for the cooling aspect. So we have additional information for the cooling load. The front end of the facility faces west, and all windows and doors have awnings. The lighting within the facility consists of 575 fluorescent luminaries, each containing 2 60-watt lamps. Within the facility, 75 men performing light work and 50 women performing light work will be employed. And the outside temperature is 97 Fahrenheit. The inside temperature is 78. So we want to cool this facility according to those requirements. So we're going to design for the cooling load. Okay, so let's look at the components for the facility, and we're going to be using the same U factors because it's the same facility. So those are not changing. So we're going to start with the floor. We have the same facility, right? So it's 250 feet by 100 feet. So the area is 250 times 100. And the U factor is the same, 81 BTUs over hours feet square. And then the temperature, now we use the outside minus the inside. So that's 97 Fahrenheit minus 78 Fahrenheit. And for the floor, we had 3.85 10 to the 5 BTUs an hour. For the roof, we have the same area, 250 times 100. The U value for the roof is 0.20. And the temperature difference is the same. So this is going to be equal to 0.95 10 to the 5 BTUs an hour. For the glass windows, we have how many? 16 glass windows, 4 by 8. So 16 and the U factor for the glass windows is 0.63 BTUs. So 0.63 BTUs hour feet square. Temperature difference is the same. So this is equal to 0.06 times 10 square. Okay, so for the doors, these again are very similar computations. The one we got for the heating load, because these parameters, I mean, the size is not changing. So this is 4 by 6, 1.13 BTUs hour feet square. Temperature difference is the same. So it's 0.02 10 to the 5 BTUs an hour. For the walls, again, we are gonna look at the size of the walls, and we're gonna subtract the size of the area of the doors and the wall and the windows. Sorry. So this the area of the walls minus the area of the doors and the windows. This is gonna be 2 times 4,500 feet square plus 2 times 1,800 feet square minus 16, 4 by 8, minus 8, I'm sorry, 4, 4 by 6. All that multiply by the coefficient for the walls, which is 0.39 BTUs an hour per square. And then the temperature difference, which is not changing, so 97 Fahrenheit minus 78 Fahrenheit. This is equal to 0.88 Okay. So next we have QB. QB is the cooling load due to ventilation. So again, here for QB, we're going to use the same dimensions that we use for, or the same components that we use for infiltration. So it's going to be the area of the roofs and the area of the wall. So this is going to be 25,000 feet square plus 12,600 feet square. All that multiply by the coefficient, 0.2 BTUs an hour feet square times the temperature difference so this is 1.43 and to the 5 BTUs an hour. Next one. We have the cooling load due to solar radiation. So for that, we have this equation. It's computed using the area of glass surface. H is the heat absorption of the building surface, and S is the shade factors for various types of shading. So these are parameters that are again based on the location and the type of materials that we are using and the location. So I'm gonna put that information here for this facility. The heat absorption for the west side of a facility in Chicago is 100 BTUs in our feet square. And for the east side, $75 BTUs in our feet square. Also, the shade factor awnings are 0.3. Okay, so using this information, we can compute the cooling load for solar radiation. So QS is going to be, again, the area of the glass components. So we have 8 double pane glass windows and 2 3x8 glass doors. 8 4x8 double pane glass windows and 2 3x8 glass doors on both the front and the back sides. So in total we have 16, but we have them located in different sides of the facility. Okay, so some of them, again, the ones in one side will be having a solar radiation, will have a different impact for the ones located on the other side, right? So that's why we're getting this absorption for the west side and for the east side, and we're going to use those accordingly. So half of the doors and the windows will be accounting for this west side absorption, and then the rest of them will be located on the east side and will have a different absorption rate. So this QS will have two pieces. The A windows that are located on the west. So we have A windows, 32 feet square, plus 2 doors that are 24 feet square. All this multiplied by the factor associated with the west, which is 100 BTUs in our feet square. Okay, so we have all that. And this is plus sorry, I forgot something. We also have to account for the shade. This is times 0.3, which is the shade factor. Shade factor is 0.3. So that's this number right here. Plus the computations for the east side, A times 32 feet square plus 2 times 24, the area of the doors, times the 75 BTUs an hour feet square times 0.3. And again, this 0.3 is the same shade factor now applies to the east side. And this QS equals 0.16 10 to the 5th BTUs an hour. So QS, again, you need to know the information for the facility in terms of the heat absorption. For the west side, east side is going to be different according to the shade that is affecting the facility. And then we also have the shade factor according to the awnings, which is mentioned that the doors have some awnings in this design. Yes. So these are part of the structure that you're using for covering the doors. Like for example, if you're leaving the facility that if it's raining or something that is not going to it's not going to fall water on top of you right away. So those are part of the design features of a door, for example, or the windows as well. Any other question? Good. So QS. Now we still have 3 more pieces to account for. The lining, the personnel. Okay, so let's look at that. So let's start with the lining. The cooling load. From lightning may be calculated using this equation right here. And it's going to depend on the type of luminary that you're using. So I will put here using equations in slide 33, 32, 31. So for equation we have the type of lighting that we are using, and we are going to compute that based on the wattage for the lights, and we're going to multiply that by this factor. In this facility, we have 575 fluorescent luminaries, each containing 2 60-watt lamps. So that's the information that we are going to use. So Q lightning, this is fluorescent. It's going to be equal to the number of luminaries, 575, but we have 2 lights in each of these luminaries. So it's times 2. The watts is 60. And the factor is 4.25 BTUs an hour watts. So for the lightning, have 2.93 10 to the 5th BTUs an hour. And then QP the cooling load for personnel. We have QP equals here for the personnel. QP is the number of men and women performing light and heavy work, and multiplying that times the heat gain factors given in this table. Okay, so in this case, we have 75 men performing light work and 50 women and 50 women also performing light work. So the parameters that we're going to use are based on light work. So it's 700 and 800. So QP equals 75 men times 800 BTUs an hour plus 50 women doing also light work. 700 BTUs an hour. And QP equals 0.95 times 10 to the 5th BTUs an hour. Okay, so now we have all the pieces. The last part or the last step is to add all these pieces to compute the cooling load. So QC is going to be equal to 3.85 plus 0.95 plus 0.06 plus 0.02, 0.88 plus 1.13 plus 0.16 plus 2.93 plus 0.95. All these to the power of the 5, and this is equal to 11.23 10 to the 5th BTUs an hour. It's a long process, right? Obviously, if you're doing it by hand, it takes longer. But the idea is, if you're gonna do this often, you can prepare some type of Excel worksheet in which you can just plug in the numbers and get the results. But doing the step-by-step process help us understand what's going on for each one of these pieces. And that's the last slide for this first part of the lecture. On the second part, we are going to talk about electrical and lighting systems and also life safety systems. So let me transition to that next part. See how far we can go. But then, again, this is a continuation of these requirements, space requirements and layout, specifically looking at the space requirements for some of the components inside the facility. and also computing some of the requirements in terms of the equipment that is needed. Yes, sir.
So with the information we just found out, that BPE rate, they can now give us an idea of what the size of the system is.
Exactly.
And now we can plan the space that we're going to use.
Exactly. So yes, so once you compute the cooling and heating requirements, then they can have an idea of how much of an equipment you're gonna need for this facility, and then they will tell you, okay, you're gonna have these, you're gonna need to have this much space to accommodate this equipment, and then you as a facilities planner will account that for your design. Yes, correct. Good question. Any other question? Good. So so again, this is a continuation of this discussion. We're gonna be looking at some of the other important aspects of the design of a facility, looking at electrical aligning systems. So here we're gonna also look at an estimate in terms of how many luminaries do you need for a facility, based on some of the requirements for the facility. And also we're gonna do a discussion on life safety systems. So what are the things that you need to account for when designing a facility in terms of life safety? The learning objectives are not changing. They're the same as the previous one. So provide an overview of how the system's elements impact the overall process of facilities planning. So all these things that you're accounting for are an important part of designing your facility. And not accounting for those can create some trouble. So so you want to make sure that you are accounting for the space requirements of all these systems, and then provide an understanding of the various system elements within the facility. So again, we are not going to build the facility, right? So we are just planning for the inside and the layout of and the requirements in terms of systems that are needed for the facility. So electrical and lighting systems, the facilities planning responsibility is to specify what level of service is required and where it's required. So what you might have different departments in your facility. Some of them will require more lighting than others, depending on the type of activity or the type of process that you are required to do in that area. The power company needs the electrical load requirement for a facility before construction begins. So that's another important part. So how much power are you gonna need? So we're gonna have a preliminary estimate. So they can say, okay, we need to do these modifications, or we need to add more power, or and so on. This is also becoming relevant now that some of the facilities are trying to balance the use of fossil fuels and renewable energy. So you can not only depend on the power company, but if your company also wants to add some renewable energy component to the system, you can also plan for that. So you can say at least 25% of the plan is going to be supported by some type of renewable energy, and then the rest will be responsibility of the power company. So the facilities planner must ensure that major load requirements, both present and future, are included in the design. So if you are going to start with a certain level of production, but you know that in the future there's some expansion that might happen, and you know that you're going to bring in some type of products that will require more power, or some machines that are going to be needed, or maybe you're duplicating your production, so you know you're going to need more capacity and more power to run those. So those things are also part of the planning. So facilities planning must ensure that major load requirements, both present and future, are included in the design data. So using this information, the design engineer can adequately size main switch gears, transformers, feeders, panel boards, and circuits to handle the future electrical needs of the facility. So here's some information about the average load requirements according to building type. So you see hospitals have a very high requirement, 3,000 watts per bed. In office buildings, plants is based on the feet square of the plant facility. So 20 watts per feet square. Schools between 3 and 7, shopping centers between 3 and 10. So in terms of, we know that plants will require more power than office buildings because we have all these equipment that is used for production purposes. So facilities lighting should not be planned by the same person planning the electrical services because illumination should be custom designed for the areas within the facility. Again, depending on the type of process that you're going to be running on these areas, you need to have some specific, or you might have some specific requirements in terms of the lighting. So we have to take that into account. So lighting system might be designed using the following 8-step procedure. So this is again a process, right? We have to take into account multiple things. So we start with determining the level of illumination that is needed for the area. So the minimum levels of illumination for specific tasks are given in table 2 that I'm going to show in the next slide. And when selecting the level of illumination for a particular workstation, the following criteria must be considered. The nature of the task, the amount of reflectivity of the workstation, components, and surrounding area, the current levels of natural or general lighting, the need for natural illumination, and also the worker's age and visual acuity. So all those things must be taken into account. Okay, so here's the table that I was referring to. This table is in your textbook, but it includes some of the tasks that you, or a list of the tasks that you might need to design for. And then the minimum illumination required in terms of foot candles. That's the former measurement. So for example, here I have highlighted the medium bench and machine work. Ordinary automatic machines, rough grinding, medium buffing, and polishing requires a minimum of 100 foot candles in terms of illumination. But you can see this is divided by different type of industry. So here we have the machine shop, we have material handling, we have offices, paint jobs or paint shops, storage rooms and warehouses, welding, inspection, and assembly. See, the maximum that you can observe here is a 1,000. It was repeated for multiple type of operations. So for example, inspection, very difficult. We also have extra fine assembly, extra fine bench and machine work. So the lowest or the highest the detail, the more illumination you might need. Step 2 is to determine the room cavity ratio, RCR. And this is an index of the shape of a room to be lighted. The higher and narrower the room, the larger the RCR, and the more illumination needed to achieve the required level of lighting. So RCR might be calculated using this equation. So we have 5 times the height of from the working surface to the luminaries, the room length and the room width, and the summation of those dimensions, and all that divided by the length times the width. So that's again the room cavity ratio. So when we say the height from the working surface to the luminaries, in this case, that would be the height between the roof, which has integrated lights, and this is my workstation. So it will be that dimension from the roof to this surface. That will be the height from the working surface to the luminaries. Number 3 is to determine the ceiling cavity ratio. So here we have some important differences. So if the luminaries are ceiling mounted or recessed into the ceiling, then the reflective property of the ceiling will not be impacted by the luminaries mount height. So the CCR need not be considered. So for example, these lights are not hanging, they're mounted in the ceiling. So in that case, there's no reflection happening because they're integrated into the roof. The greater the distance from the luminary to the ceiling, the greater be the CCR and the reduction in ceiling reflectance. So if that's the case, then we have to compute this ceiling cavity ratio. And this is equal to the height from the luminaries to the ceiling. Again, if they're hanging, you have to measure that distance between the roof and the lights. Multiplied by the room cavity ratio, which we computed in the previous slide, all that divided by the height from the working surface to the luminaries. So this is going to be hanging. You need the distance between the luminaries to the ceiling and the distance from the luminaries to the working surface. Step 4, determine the wall reflection and the effective ceiling reflectance, ECR and WR. The wall reflections and a base ceiling reflectance value can be obtained from table 3. So this is table 3. Depending on the type of materials that we are using, white paint, light color paint, approximate reflectance about 80%. And then depending on the other, like brick, cement, and concrete, it's gonna have only 35. Black paint is dark paint is gonna be very low. So again, this is depending on the material. So for example, these walls are not white, but they're very light color, so the reflectance should be higher than if we have very dark color walls. So here's so once we have the information about the CCR, the BCR, and the wall reflection, we can determine the ECR based on all combinations of those combinations of CCR, WR, and BCR. So the percentage or the percent effective ceiling reflectance, ECR, for various combinations of ceiling cavity ratios, wall reflectance, and base ceiling reflectance. So again, for the effective ceiling reflectance, we had to use all those other factors that we computed. So if we have a BCR of 10 with a WR of 50, and then a CCR of, I don't know, 2, then the number for the ECR will be 13. Okay, so we're gonna have this tabulated information that is gonna take into account the BCR, WR, and the CCR in order to get that effective ceiling reflectance. So we'll see that with an example, just guiding you through the process. So, so if the luminaries are to be ceiling mounted or recessed into the ceiling, the ECR is equal to the BCR, right? Luminaries are to be suspended, the ECR is determined from the CCR, WR, and BCR using this table. So keeping track of all these factors is important because then at this point, you're gonna be using all of them. Step 5 is to determine the coefficient of utilization. This is the ratio of lumen reaching the work plane to those emitted by the lamp. It is a function of the luminaries use, the RCR, the wall reflection WR, and the effective ceiling reflection ECR. The CU for standard luminaries is given in table 5. So again, we're going to look at the type of luminary that we are using, the spacing, and then these factors will help us determine the right value for the coefficient of utilization. Step 6, determine the light loss factor. The two most significant light loss factors are lamp lumen depreciation and luminary dirt depreciation. So if the lamps are gonna be depreciating in any way, like after a certain amount of time, and if they're gonna be dirty, then we have to take into account that, or there's a possibility of them becoming dirty. The lamp lumen depreciation is the gradual reduction in lumen output over the life of the lamp. Typically, lamp lumen depreciation factor is expressed as the ratio of the lumen output of the lamp at 70% of rated life to the initial value. The lumen output for various lamp givens are given in table 6, including the lamp lumen depreciation. Therefore, no additional consideration is needed. Luminary dirt depreciation is the light loss associated with the conditions under which the luminary operates. The luminary dirt depreciation varies with conditions and the length of time of the cleanings. So we have that information. Table 6 had the lamp output at 70% of the rated life. So depending on the type of lamp that you're using, the watts, we got that 70% rated life. And then we have the luminary dirt depreciation factors. So depends on dirt condition. So if you're in the office, you're gonna be looking at this side of the table. If you're in machining conditions, you look at this one. High-speed printing, medium machining, and very dirty foundry or heavy machining. So depending on what type of manufacturing process or facility you are designing for, and then you have an estimate in terms of the cleanings, months between cleaning, and then the type of luminary that you're using. And the combination of those help you determine this depreciation factor. All these factors are already tabulated. Just have to make sure that you get the parameters needed to find the right point. And then using all that information, then we can calculate the number of lamps and luminaries. We'll use equation 3 to calculate the number of lamps and equation 4 to calculate the number of luminaries. So we have the number of lamps is just a multiplication of the required level of illumination, the area to be lit, the C coefficient of utilization, the LIF, and the lamp output at 70% of rated life. So we get the number of lamps, and then with the number of lamps, we can compute the number of lamps per luminaries, and that will give us the number of luminaries. And then step A will be to determine the location of the luminaries. And here we have an example. So let's see if we can work through this. So in this, we have a shop with these dimensions, 100 by 40, with a 13 ceiling will be illuminated for automatic machining and rough grinding. Uniform lighting is required throughout the machine shop. If the luminaries are to be ceiling mounted, all ceilings on walls are to be painted white, and all luminaries are to be cleaned every 24 months. The question is, what lighting should be specified? So let's work through this. So we're going to start by determining the level of illumination. So here we have an automatic machining and rough grinding. So we go to table 1. That's why I highlighted this one. So for the example, this is the setting, and this is the minimum we need, 100. So the level of illumination is 100 foot candles. Step 2, determine the room cavity ratio, the RCR. And we are going to assume that all working surfaces are 3 feet from the floor. Okay, that information was not given, but we are going to assume that as average, 3 feet from the floor is the surface of the working stations. So the RCR in order to compute the RCR is 5 times the height from the working surface to the luminaries, the room length plus the room width divided by the room length times the room width. So the RCR is going to be 5 times 13 feet minus 3 feet. The roof is 13 feet. Difference between 13 and 3 is 10. So 13 minus 3. And then we have the area is 100 feet plus 40 feet. And the multiplication of 100 feet times 40 feet. So this is equal to 1.75. Step 3, determine the CCR or the ceiling cavity ratio. In this case, the CCR need not to be considered because the lights are ceiling mounted. So need not to be considered. Because lights are ceiling mounted. Number 4, determine the wall reflection and the ceiling effective ceiling reflectance. So determine the wall reflection and the effective ceiling reflectance. According to table 3. So let's look at table 3. We have a white paint color, light color, right? That's the type of walls that we have in our facility. So the approximate reflectance is 80%. So WR so here we go. WR can be obtained from table 3. So both of them are 80%. So WR and BCR are 80%. And because the luminaries are to be ceiling mounted, the ECR is also 80%. Based on our discussion. So if they're ceiling mounted, then they're gonna be the same value as the WR and BCR. Okay, let me show you that. So if the luminaries are gonna be ceiling mounted or recessed into the ceiling, the ECR is equal to the BCR, right? So that's the case. That's 80%. They're ceiling mounted, so the ECR is also equal to 80%. What's next? Step 5. Determine the coefficient of utilization. Okay, so step 5. Determine CU. So if fluorescent lamps in uncover fixtures are to be utilized, the CR can be interpolated from table 5 as being between 0.88 and 0.78. So if we're going to use fluorescent lamps in uncovered fixtures, I can go to table 5. And using this type of fluorescent lamp, and based on an 80% WR, RCR is also, what's the RCR coefficient 1.75. So it's between these two. So the value will be between 88 and 0.78. So fluorescent lamps, RCR is 1.75, so it's between these two numbers. We have a WR of 80%. So the number is between these two. You can use interpolation to find the value for 1.75. If you don't want to interpolate and you want to use the closest one, that will be 0.78 because it's closer to 2. But with interpolation, that value, a coefficient of utilization of 0.8 will be used. And if you have a calculator that can be programmed, you can do interpolation very easily. Step 6. Determine the light loss factor for fluorescent lamps in uncovered fixtures in a medium dirty environment that are cleaned every 24 months. A lamp luminary dirt depreciation factor of 0.85 may be obtained from table 7. Okay, so we have fluorescent lamps. In a medium dairy environment. And they're clean every 24 months. Okay, so that's given, right? Every 24 months. So if we go to table 7, this light machining every 24 months. And we have fluorescent lamps in uncovered fixtures. That's 0.85, right? That's this number. How do I go back? So every 24 months, median environment, fluorescent lamps in uncovered fixtures. This is LLF. So LLF equals 0.85. So last step, finally, we get to compute the number of lamps and luminaries. So using all this information, the number of lamps will be equal to 100 times 100 times 40 divided by 0.8 times 0.85 times 3,300, and this is equal to 179. So basically what we're doing here is just plugging in the values that we got from this process into the equation, and we get the number of lamps. If you want to know the number of luminaries, you have to divide by how many lights you're going to have per luminary. So if you're going to have 2 per luminary, you have to divide by 2, and it's going to tell you the number of luminaries that you're going to need. And I think, yeah, let's stop here. I think your assignment, the one that is due on Wednesday, has a problem like this one. So you needed this discussion to complete the assignment. And then we will complete this lecture on Wednesday. Any questions? Nope. So I'll see you Wednesday.